Good morning to Ms. Lister. I'm Wishley Dasi representing ES7 Group 9. Before I explain about micromobility, let us check out what's our background. We all know that UTP is a huge campus. Based on information from UTP website, UTP is nestled in 400-hectare area. Due to the large size of our campus, students are facing some problems. Example, going from Village 1 to Pocket D took almost 10 minutes by walking. As a result, many students started to ride bicycles to shorten their transit time in campus. So, our case study is to determine which type of bicycle is more suitable for students to ride in UTP campus. The main topic of our case study are rotational motion and dynamic and force.
In this project, our first goal is to determine the period taken for the bicycle to travel a predetermined distance on both flat and steep terrain. Next, we want to dictate a wheel's mechanic of rolling motion by calculating its angular and linear velocity. We also aim to differentiate the effects of moment of inertia for different wheel diameters toward the generated torque. Last but not least, we will decide the most optimal micromobility based on the calculations for their respective power.
Let us continue with the theory and formula. First, we will look at the angular speed. What is angular speed? Angular speed refers to the speed of the object in a rotational motion. Angular speed is denoted by the symbol of omega and it is measured by the unit of radian over the second. Okay, next we continue with the tangential speed. Tangential speed is the velocity of a specific point of a spinning wheel which is tangential to the rotation of the wheel. Tangential speed is denoted by the symbol of velocity which is v and is measured by the unit of meter over the second. Tangential speed changes based on the distance of the point to the center. This means when the radius is increased, the tangential speed will also increase. Okay, next is friction. Friction is the force which acts opposite. The key point is opposite to the movement on an object when it is contact with the ground. For example, when the object is moved to the right, so the friction force is to the left. Okay, friction will increase depending on the roughness of the surface and it is measured by the unit of newtons. And lastly, slipping or skidding. Slipping or skidding happen when a wheel experiences a linear displacement whilst not rotating with a correlating angular speed. For more clearer, it happens when the brake is applied. So, the wheel not rolling but it is skidding.
For the scenario is that Ali has two different bicycles with different mass and also different radius of the tire. Now we need to determine the most suitable bicycle to be used in the campus. First, we need to determine the RPM when both bicycles travel at constant velocity of 10 meter per second in a straight line. We need to assume that there is no air resistance. Now for the solution, the RPM can be calculated by using the formula V equal to omega R, and then we can achieve the omega of each bicycle. For the first bicycle, it is a bit higher than the second bicycle. Now we also need to determine which bicycle require more work to travel a quarter of a mile at constant velocity of 10 meter per second from rest. To do this, we need to find the moment of inertia of each bicycle by using the formula mr squared. And then we also need to find the angular acceleration of each bicycle when going from rest to the desired 10 meter per second. Now we can find the torque needed to run the bicycle, and also the torque can lastly be timed with the angular displacement when going a quarter of a mile to find the work needed to travel a quarter of a mile for each of the bicycle. We can see that the second bicycle will require more work to travel a quarter of a mile. Now we need to determine what is the maximum braking force of that bicycle in order to avoid sliding or skidding on the road. To determine that, we know that the bicycle is travelling at a constant speed, which means that there is no acceleration. Therefore, we can conclude that the braking force is equal to the friction force. And to find the braking force, we need to just find
let's
the
explore the fascinating world of rotational dynamics.
88.29 Newton.
Today we'll be using two bicycles with different diameters and thickness to demonstrate how rolling motion interacts with terrain changes like that one. Wait, can you guys see it? I'm in this slope! However, due to the difference in diameter and thickness, the linear acceleration may differ. Now let's compare our bicycles based on these crucial aspects. The bicycle with larger diameter will experience longer period, lower angular velocity, and higher linear velocity for the same rotational speed as this bicycle. In theory, both bicycles will experience the same angular and linear acceleration because of the gravitational pull. However, the bicycle with larger diameter will experience higher moment of inertia, meaning it has higher resistance to its motion, requiring a significantly larger amount of torque to exert the same amount of force. both bicycles will require the same power input to maintain the same speed, as power depends on both force and linear velocity. Now let's gather some data points from these two bicycles.
Choosing the right bicycle for your university campus? Consider your terrain. A smaller diameter might be more agile for navigating crowded spaces, while a larger diameter might be more comfortable for longer distances and slight inclines.